So we've been talking about fuzzy logic, fuzzy sets, fuzzy linguistic variables. It does turn out that us as human beings communicate with fuzzy linguistic variables all the time. We tell a car to back up, and we give it kind of fuzzy directions. We describe people as short, tall, fat, ugly, yet really there's no quantities behind this. And with certain things, you can quantify it, such as fat, tall, but you can't quantify ugly. You can't quantify beautiful. And as we mentioned last time, you can't quantify quantify, I should say. Those are so-called non-ordinable or ordinable fuzzy variables. And so they can't be measured other than by our heuristics and our intuition. One of the biggest things that you learn in engineering is you go through all of this theory, and then you find out that there's one instantiation that is usually used. I'll give you an example of control theory. You go through all of this control theory stuff, and then you learn that you go out in the field, and like 95% of the embedded software or the control theory that's used is the so-called pin control theory. And that's probably 90% of the application. This is true somewhat with fuzzy logic. And I want to present today the common use of fuzzy logic, and maybe one of the most widely used of the ideas of fuzzy logic. It was pioneered by the Japanese and was adopted by America. Even there, it was not adopted, or it was not accepted very well. I had a good friend he was one of these head engineers, a fellow at General Electric, and he was the one responsible for incorporating fuzzy control in washing machines. And we talked about last time about this guy Bitmead in Australia that didn't like the idea of fuzzy control. He wanted to go back to this esoteric, more analytic control theory. And the guy's name was Piero Bonasani, and he had a really good attitude. He had people that were pushing against him, didn't like fuzzy control. And after he released the washing machines for General Electric, I think that was their first product, I'm not totally sure. But after they released the washing machines, he had people come up and said, you know, I've looked at the technology here. They said, heck, I could have done that I could have done that with conventional control, you know, and Bonasani had just a classic answer. He said, great, go do that. In other words, he didn't try to defend it. And I think in engineering, again, when you reduce things to practice, there's no arguing. And that's what the Japanese did. That's what Piero Bonasani did at General Electric and at a number of other places. So let's go over the so-called Mamdani control. And we're going to go over this in general. Then after we're done with that, we're going to drill down a little bit into the fuzzy control or fuzzy set theory. We've only hit the tip of the iceberg, and I wanted to drill down a little bit into the different examples that you can use for disjunctive and conjunctive operations, ands and ors, and also for complements and other things that have been proposed to be used. We will stick for now with the mins and maxes for the correspondingly intersection and union, and the 1 minus for the complement, 1 minus the membership function. But again, there's lots of other ways to do that, and we'll explore this after we get through Mamdani control. So with that, let me share my screen, and hopefully you can see here now. Can you see the fuzzy inference Mamdani control? And I'm just going to run through an example of how you might set up an expert system. Everybody see it? Give me a nod. Okay.
Dr. Marks, on mine, it's a little cut off. The O in control is the furthest right that I can see.
Is that right? Okay, I see this little green box, and I'm not sure what the heck's going on. I've never had this problem before. Let me try it again. Okay, is it? Yeah, it's still cut off though, isn't it?
I can now see the whole window, but it's not in full screen mode.
Okay, can everybody see the whole window? Okay, you can see the whole window. Okay, so that's good. Okay, so we have the fuzzy inference, and this is the so-called Mamdani control. I'm going to show you how you might set up a very simple expert system based on fuzzy linguistic variables. And I'm going to assume that we want to set up an expert system that admits undergraduate people into graduate school. Now, typically there's more than two variables. We're only going to deal with two variables, and then we'll talk about the generalization of this idea to higher variables, higher number of variables, a greater dimension, if you will. But we're going to look at just the statistics of the GPA, the grade point average, and your GRE test. Your GRE test is how well you did on the general admittance that is sometimes required. I don't know if we require it anymore. I think that we might, but the GRE is kind of the great leveler, because if you get a bachelor's degree at one place in electrical engineering and then somebody else gets it at a different place, the grading systems might be totally different. There might be grade inflation at one and not grade inflation at the other one. So the GRE was always looked at as a leveler, and that's the way it is. So let's go ahead and look at Mamdani control with the example of the GPA and the GRE as the fuzzy linguistic linguistic variables. Here's the rules that we want to put together.
Dr. Marks.
Yeah.
Sorry, on my screen at least. I don't know if you're in full screen mode on the PowerPoint, but it's just showing the non-full screen mode window, and it's moved down so that we can only see the top.
Okay, so this is not good. Okay, let me try to share it in the non. I have no idea what's happening. I've never had this problem before in my life. Let me try this. Okay, it automatically went to. Huh. Well, who'd have thunk? It went to, okay, can you see anything now?
I can see the non-full screen PowerPoint window, and I think all of it on slide 2.
Okay, I don't know what a conus quint is. It should be a consequent. So can people see this screen now? Can see the entire screen? Okay. Again, I don't know what happens. Fuzzy rules usually have what's referred to as an antecedent and then a consequent. And the antecedent is usually of the form if, and then you state an antecedent, then you have a consequent. And so we can generate a number of antecedents and consequents for admission to the graduate school using fuzzy linguistic variables. So let's go through and see if we agree with these fuzzy explanations. If an undergraduate's GPA is high and their GRE score is high, then an undergraduate student will make an excellent graduate student, right? That would be a good rule. Or if their GPA is high and their GRE is fair, or their GPA is fair and their GRE is high, then an undergraduate will make not an excellent, but a good graduate student. Notice all of the fuzzy linguistic variables there: fair, high, good, excellent. This is just a heuristic explanation of how we might want to admit them. And notice there's an or here. We have an and here in the antecedent. If their GPA is high and their GRE score is high. So not only do we have the fuzzy linguistic variables, but we begin to have the logical operations that we talked about in terms of ands and ors. So the next fuzzy rule is as follows: or, and notice all of these are mutually exclusive, right? You can't have one and have the other. You have to follow into one of these categories. Or if their GPA is fair and their GRE is fair, then an undergraduate student will make an average graduate student, or otherwise the undergraduate student will make a poor graduate student. So look at those. Don't those make kind of sense in a fuzzy variable sort of idea? We're explaining the way that the criteria that we would put if we went to an expert. We did talk about expert AI systems, and Mamdani control is kind of an expert system because we write these down. These rules came from somebody with expertise, but then somebody has to come along and they have to quantify these things which have which the expert has laid down. So it's our job now to reduce this to software, if you will, to a program or an algorithm. Okay, we're going to simplify this, and we're going to simplify this next. Well, shoot, how do I change screen? I guess I click over here. I'm going to kind of abbreviate those same fuzzy inference rules. Like if the GPA is H high and the GRE is high, then you're going to have an excellent student. Or if the GPA is high and the GRE is fair, or the GPA is fair and the GRE is high, then you're going to have a good graduate student. So you see, I've used kind of hyphenated words here. If the GPA is fair and the GRE is fair, then you have an average. Then you have an average. Can everybody see, by the way, you can't see my cursor, can you? Or can you? You can see the cursor, okay. Then average, or if the GPA is poor or the GRE is poor, then P. Now notice we can lay these rules out in what is called a rule matrix. We have over here a GPA of poor, fair, and high. We have a GRE here of poor, fair, and high. And each one of these is a antecedent, each pair of these. So we have a total of nine possible antecedents, if you will, if we look at all of them directly. So if we have, for example, if the GRE is poor, you know what, I'm going to try to get my screen here, see if this works. The overwrite screen. Okay, of course, it isn't working, so I have to unplug it and plug it in and see if anything happens. Nothing happened. Let me try one more time. Usually I hear a little boop, boop, beep in the background, but I'm not hearing it now. Okay, well, I guess that isn't working, so we'll have to make do with my cursor. Well, so much for technology, I guess, right? Okay, well, I'll put this to the side then. But I want you to look at this and make sure that you can see that this matrix on the right is an equivalent statement of the antecedent and the consequent. And again, consequent. By the way, if you look at the Google Sheets, I've placed a link to these slides so you can get them and look at them if you so desire. So do we see that? We see how it can be related to a matrix, a rule matrix, if you will. And in Mamdani control, setting up this rule matrix is a big part of the job of the expert. And so that's what they do. And so this is this statement. Now we have to decide what we mean by poor, fair, and high. It turns out that this is a process known as fuzzification. And yeah, it's a for real word. They use it in the literature, fuzzification. Later on, we'll get into a weirder word, which is defuzzification. But fuzzification takes a single value and it expands it into a vector of fuzzy numbers. Let me give you an example here. We're going to choose, first of all, the fuzzy membership function for the GPA on the bottom left, you can see here. So these are the membership functions for the GPA. And we have three different membership functions corresponding to poor, fair, and high. And the GPA goes between 0, 0 and 4.0. So you can see that these are fuzzy membership functions. So the ultimate fair is a grade point of a 3.0. You can see that the membership function for fair peaks out at 3.0. And so this is the membership function for the GPA. On the right, we're assigning fuzzy membership functions for the GRE. And I'm assuming here that the GRE is measured from 500 to 800. Just bear with me if this is not the case. But this is a membership function for your final GRE score, differentiating between the poor GREs, the fair GREs, and the high GREs. Is that okay? Each one is a fuzzy membership function. It is the relevant value that is taken on for a specific instantiation of the GPA and GRE. So here we go. We set this up, and let's suppose that we had, for example, somebody came along and they had a GPA of 3.5 and their GRE was 725. You see that? The question, and what we need to do now is we need to take those two crisp numbers, a 3.5 on the left for the GPA and a 725 on the right, and we must expand it into a fuzzy vector. And you can see on the left here, this 3.5 doesn't even intersect the poor curve, right? So there's zero membership. It's totally, the 3.5 is totally outside the set of poor GPAs. As far as fair and high GPAs, it's both 50-50. It's right on the edge, right? So that's what we get in the upper right here. In the upper right, we get that the membership function for the poor GPA is 0, for the fair GPA is 0.5, and for the high GPA, it's also 0.5. So we've taken that crisp number, we have fuzzified it into a vector of fuzzy numbers corresponding to the element in each one of the different sets that is defined. We're going to do something similar now here for the GRE. The GRE is 725, and you can also see that this does not intersect the poor GREs. So if you look at this, it turns out that if we look at 725, it intersects the high GRE at about 1/4, and it intersects the fair GRE at around 3/4. And those are the three vectors that we have here. So this is the fuzzification of the 725. So again, we have the fuzzification and the relative membership functions in all of the defining sets. Now, you'll notice here that we have something very interesting. We have two goods here, right? And here's the way to think of this as good. A student is good if H is equal, H is 1/2 and F is 1/4, or it's good if the GRE is high and the GPA is fair. You get that? So there's two ways that we can get the matrix entry for good here. It's either one of the two coordinates or it's the other two coordinates. Each one of those two coordinates points to a separate red box. So they're good if one is true or the other is true. What is the Zada fuzzy or? Maximum, right? Something or something. We take the maximum of the membership functions. So therefore, if we're forced to assign a number specifically to good, we just take the maximum of all the goods, because it's good if this is true, or this is true, or this is true, and we just take the maximum because that's what the or is. The other thing we need to do now is to figure out the membership function, the fuzzy membership function for the consequent. Thus far, in the upper right-hand corner, we have the vectors for the fuzzy membership of the antecedents, right? These are the antecedents. And we need to figure out the consequent membership function, which is shown on the left. Now, I want you to notice about talking about the inner product, or the outer product, I'm sorry, of two fuzzy vectors. Remember, we talked about, for example, cities far from LA and liquids that tasted good. and we took the outer product, and it was kind of totally meaningless. Here we're taking the outer product and it's meaningful. So we have, for example, let's take this bottom right where we have excellence. Well, the student is excellent if the GPA is high and the GRE is high, right? Bottom right, the student is excellent if the GPA is high and the GRE is high. What's the and operation? It's minimum. So we take the minimum of 1/2 and 3/4, that gives us 1/2. So that's the membership function of the GPA being high and the GRE being high. 1 is 3/4, 1 is 1/2. And the student is excellent if the first one holds and the second one holds. The and corresponds to a minimum. So that's the reason we do a 1/2 here. So each one of these entries is the minimum of its corresponding X and Y values. Here, for example, we have H is equal to 3/4, F is equal to 1/2, and that gives us a value of 1/2, since that's the minimum between the two. Because the student is good if the GPA is fair and the GRE is high. And the GPA being fair is 1/2. The GPA being high is 3/4. The minimum of that is 1/2. So you can see what happens. We fill in the matrix by going down each element and taking the minimum. If we use the Zeta intersection, we use the minimum between each of the results, each one of the X and Y values. Does that make sense? Now, usually if you take a vector times another vector, and you take the outer product, what is the outer product? It's 1 times the other one. We'll find out that the minimum in the intersection is kind of like times, it's kind of like times, except it is the minimum. So we have a lot going on here, and we fill in this matrix. And after we fill in the matrix, we have 2 elements for good. And if somebody points a gun at our head and says, well, is good 1/4 or is good 1/2? And repeating what I said before is that, well, it's good if the first red box is true or the second red box is true. Well, what is the or? The or is equal to the maximum. So therefore, we would take the maximum of those 2, and the maximum would be equal to 1/2. Any questions on this? You kind of see what's going on, hopefully?
Dr. Marks, I don't know if you plan to explain this in the future, but the bottom left graph.
Okay, I'm gonna get that now.
All right, just make sure. Okay.
Yes, we have to figure out what the membership function is for the consequent. We have the fuzzy membership functions for the antecedents. Those were the 2 membership functions that I showed before. And let's see, how many outputs do we have? We have outputs, consequence. We have poor outputs, average, good, and excellent, right? If you look at this matrix here, either one of the matrix, we have, let's see, 1, 2, 3, 4 different possibilities: poor, average, good, and excellent. So we need to define membership functions for the consequent of poor, average, good, and excellent. And what I've done here at the bottom left is I have graphed out what might be, for example, a membership functions for good, for poor, average, good, and excellent. And the thing is that what's going to be our x-axis? What are we going to measure here? What are we measuring? Well, we're kind of measuring on a scale of 1 to 10 whether the student would be a good graduate student. So that's going to be my scale. You notice that the x-axis is from 0 to 10, or 0 to 10, but figure it as 1 to 10. And so it's like the regular fuzzy membership function where you judge something on a scale of 1 to 10, like your pain, for example. So we're going to try to figure out on the scale, and we're going to see that, if it's close to 10, it's going to be a really excellent graduate student. If it's around 7.5, well, it's a good graduate student. Average is about a 5, And poor is, well, you can see the left hand sequence there. So we're trying to rank these students. And you'll notice if we apply this to a number of different students, we would have a spreadsheet and we would have a ranking for each one of the students as determined by this expert system. And we could literally take them and arrange them into increasing order. And if you went totally by the numbers, which I think is a terrible thing to do, but if you went totally by the numbers, you'd probably assign a threshold, accept everybody above that, and reject everybody below that. Maybe the threshold is determined by your number of open slots that you have in your results. So that is what this is about. Okay, that's what the bottom is. Notice it's labeled the consequent membership function. So let's review. We have the fuzzy rules, and we've assigned for this one person with a I think it was a GPA of 3.5 and a GRE of what was it? GRE of 725. Okay, so this person comes in and fills up the matrix this way, and we have the result here on the bottom, as you can see. Okay, so how do we figure out where we are in this x-axis? That isn't clear. One of the ways to do it is just to figure out the maximum. What's the maximum here? Well, we have a tie for we have a tie for the maximum. The maximum membership function for good is a half. The maximum membership function for excellent is a half. If those weren't tied, we might just take the biggest. What we'd like to do in general is we'd like to come up with a measure of central tendency here. Central tendency is something you hear about in probability density functions. If you have a probability density functions, central tendency would be kind of where the distribution is centered. And you can either have it at the maximum or the mode, right? You can have it at the mode, which is the maximum. You can have the mean, or you can have the median. All three of those are different measures of central tendency. So we would like to look at these entries in the matrix here and come up with some measure of central tendency. If indeed you went by the mode way of doing it and just chose the maximum, you would say that, well, good is a half and excellent is a half. So I don't know, the student is halfway between good and excellent. If there wasn't a tie, you could just choose the maximum if you chose the mode way of doing things. That isn't the way that Mamdani control is typically executed, and we're going to go through how that is done right now. We are going to take all of these labels. P is equal to 0, A is a quarter, G is a half, and E is a half. I don't know if you can remember that, but you have 0, a quarter, and a half. I'm sorry, 0, a quarter, a half, and a half. And we need to take these weights and come up with a defusification. We need a number in the end, which is between 0 and 10. Well, I don't know what happened here. Here's one way to do it. We're going to take each one of the membership functions and we're going to weight it by the value of the consequent. We're going to weight it by the value of the consequent. Therefore, P is equal to 0. So we're going to take this poor membership function and we're going to weight it by 0. So it doesn't come out at all. Average is a quarter. So we're going to take this value here, this membership function here, and we're going to weight it by a quarter. Is that okay? And then for good is a value of a half. So we're going to take the good membership function and we're going to weight it by a half. And then the same thing for the excellent graduate or the excellent graduate student. So we weight these and okay, so what? What does this mean? Well, the next thing we want to do is we would like to simply add these together. And here comes the idea of method of central tendency. We would like to add these together. And if you add these three curves together as they're weighted, you get the curve which is shown in shaded. So that's the curve you get. And we would like to figure out the point of central tendency. In other words, where is this lie? I think a good way to think about this, if you remember mechanics, the first moment of a beam is equal to the point of balance. So if this was a beam which was cut out of wood, and we wanted to look at where this thing balanced, we would compute the first moment of it. Same thing with a probability density function. The first moment is the mean for a probability density function. And so a typical way of doing this is figuring this out. And it turns out that this, right now, this point of balance is about a 7.2, which means that on the scale of 0 to 10, this student ranks as a 7.2. That's his ranking after the defusification. And you notice we have done defusification. That's it. That is Mamdani inference, Mamdani control. Just like anything in fuzzy logic, there is a number of different ways that you can implement this. We used min and max. You don't have to use min max. You can use some product inferencing. We're going to go through some other types of inferencing that you could go through. And it also is true for the defusification. We mentioned that we could do mode defusification, where we just chose the biggest membership function in this matrix. That would be a mode. We could use this central tendency here, where we weighted each one of these, and that works very good. You'll notice something very interesting about this is the centroid of mu sub n. We're used to, in probability density function, just integrating x times the density function, and that gives us the mean. Do you remember that's the definition of the mean in probability density function? The integral of x times the density function. Well, that only works if the area of the density function is 1. It turns out in this case, that thing we're trying to measure the central tendency of doesn't have an area of 1. So we have to normalize out the area. So the measure of central tendency for the nth membership function is given by the relationship here. The numerator you'll recognize is familiar. That's exactly what we would see from probability theory. The denominator just divides by the area, essentially normalizing the operation so that this thing that we're finding the measure of central tendency of has an area of 1. We're just normalizing it to the area of 1. And this turns out to be the centroid of mu sub n. If you do take mechanics and figure out first and second moments of beams and things like this, this is exactly the result that you have, okay? So the overall centroid is going to be equal to C, which is now notice the centroid is something which is determined totally by the membership functions. The centroid doesn't change with respect to problem to problem to problem. The centroid is always the same. It's a characteristic of the choice of membership functions that we have here. So the membership functions stay exactly the same. And that's something that you can compute offline. There's no reason to compute these integrals every time. You can compute just the C sub n, stick it in your pocket, and use it over and over and over again. What we're going to have then is the final centroid is going to be equal to the summation of the weights. These are the weights of the consequences times the corresponding centroid. And this turns out to be a very, very simple thing. It's simple because of the idea that you can generate a centroid, again, stick it in your pocket and only have to do it once in your life for a fuzzy inference system. And then you never have to compute integrals again. You just have to know what the C sub n's are. And they're dictated by your choice of your membership functions. And then you take the weights of your consequence, multiply them by the centroid, and you simply add them up. And that turns out to be the corresponding consequent. That's the total central of, that's a total measure of central tendency, the point of balance, if you will. Just like everything, you could use different means, different maxes, I'm sorry, different ands, different ors. You can also use different methods of defusification. I'll show you another one that was used. I don't think it's a very wise one, but it's called clipping defusification. The idea here is that what we're going to do with the membership functions, instead of weighting them by their corresponding consequent value, we're going to clip them at that point. So the average is going to be clipped at 1/4, and that's what we see here on the right. It's clipped at 1/4, and the other two are going to be clipped at 1/2. And then just like, so it's a very different way of doing it. In both cases, you're kind of diminishing the impact of the membership function as the weight goes down, as the consequent membership function goes down. So it makes sense. It just seems to me that this is more difficult to compute than some of the other stuff. But just like before, you would add these up. If you added up these clipped values, you would get the curve, which is shown here under the shaded curve. And that I don't know what the centroid of that is, but that has a point of balance, if you will. Also, you could look at this centroid curve and you could do a mode, right? That's a measure of central tendency. So it looks like the mode is around what, here? So you could figure out that, it's around, I don't know what that is, 8.59, something like that. So again, all of these are different possibilities. Now, you look at this and you think, wait a minute, there's too much wiggle room here. There isn't the precision that we have that we're used to in design. There isn't an Ohm's law, which is invariant, that always stays the same. We have all of these degrees of freedom. Here's what happens in practice, that a fuzzy system, a fuzzy control system, or a fuzzy inference engine, if you will, is used to perform, say, the operation of a washing machine. And you just do it by the seat of your pants. And then you go to the washing machine and you try a bunch of trials and you say, this isn't quite working right. It's doing something, it's washing too long. So you can go back and you can mess around, for example, with the membership functions. They don't have to all be the same. Some can be skinny and narrow, some can be big and fat. And you do an iterative design until you get the fuzzy membership function or the fuzzy inference system to work well. And this is true of all design, as we mentioned, with Formula 409 and WD-40. We mentioned that in here, right? All design is iterative. So fuzzy systems themselves must be iterated. You come up with your choices for the fuzzy inference about whether it's the min or the max or whatever. You choose your method of defusification, then you try it out. It doesn't work. You go back and you tweak it a little bit. It's still a little bit off. You might have to go back and play around with it a number of times. The amazing thing about fuzzy inference and fuzzy systems is that independent of these different choices of operations that you can get, you can usually iteratively design around your choices to get the fuzzy inference system to work. And that's the reason, that's why we can live with the slop. And in a way it's slop. In another way, it's just choices of different ways of doing it. But once you make a choice and you're within that realm, you can fine tune within that realm, which is fixed, in order to optimize your performance. So that's the reason we can be so sloppy in some of these different results. Let me give you an example, for example, of speed control using Mamdani control. We have a car and the car has a certain speed. It usually has a target speed. If you've used fuzzy control, or if you've used cruise control, you set your speed, right? You set the speed that you want to go. And so what you do is you take the difference between what you got and what you want, and that's the error. What you got is your speed. What you want is the target speed, and that's the error. And then it also turns out that in practice, to look at the change in error is also a good thing to do. So we look at the error, the speed error, we do a delay and look at, say, the speed, I don't know, a half second ago or something like that, and take the difference of that. And that is kind of like the first derivative of the speed error. So we're not only generating the speed error, we're doing the change in speed error. We place this into a fuzzy controller. And what does that mean? Well, we take the error, we take the change in error, we fuzzify it. We go through our rule matrix, which we have to set up. Then once we get that result, we defuzzify it, and that gives us a specific single number. that single number is how you should control your accelerator, whether the accelerator goes up or down. It's a very simple control, and it's one that can be done with a PID controller. But fuzzy is, it's so cute. Why not use fuzzy if you can? Here is an example of a possible rule matrix for changing the acceleration. Here is the error, and here is the change in error. So let's look at and see if this makes sense. Say if your error is 0 and your change in error is 0, what should your change in acceleration be? 0, right? Yeah, it means you're right on track. You don't have to worry about it. So that's what the 0 means. And the other things in here mean SP is small positive, LP is low positive, very low positive, N is negative, large negative, small negative, 0. So this is a rule table for a possible rule table for a speed controller, a cruise controller. And let's look at the extreme. So suppose that your error is a large negative, but your change in error is a large positive. Well, if one's a large negative and the other one is a large positive, if you leave it alone, it'll take care of itself, won't it? Right? If you leave it alone, it's going to take care of itself. So and you can go through and you can reason all of these. If the error is positive and the change in error is low positive, then you want a low negative acceleration. In other words, just put on the brakes or take your foot off the accelerator and let the friction take over. So this is a rule table that might be used, for example, for a speed control, and is put together very heuristically. It's put together just by examining the problem. And as before, we would look at the error. We would look at the change in the error, and we would have to have fuzzy membership functions for each of these, wouldn't we? And each one of those fuzzy membership functions each one would be applied, and we would take each result and we would come up with if you will, the membership function in each one of the corresponding categories here of the error and the change in error. And so this is an example of Mamdani control as it is applied. One of the beautiful things about Mamdani control is that, in fuzzy control, is that it's applicable in nonlinear systems. You'll notice there's nothing here which dictates you can have linear systems. If you do something like Laplace transforms and look at migration to poles and pole zero plots, if you have a Laplace transform, you're assuming a linear time invariant system. Because if you don't have a linear time invariant system, you can't do a Laplace transform. Laplace transforms assume a linear time invariant system. And therefore, anytime you have a nonlinear system, then no, that ain't going to work. Maybe if you have something which is almost linear, it'll kind of work well. But if you go to non-linear systems, it doesn't work well. The classic case is linear induction machines. Linear induction machines were invented basically by Nikola Tesla. And one of the problems with linear induction machines, they're machines without brushes, is that number one, they are time varying. In other words, once you get the thing going, it might operate a little bit different in the future than it does now. So you have the time variance problem, plus you have the nonlinearities. So all of the control theory that you learned about x dot is equal to ax plus bu, all of that assumes linearity. And if you don't have linearity, none of that stuff works. Have you seen the x dot is equal to ax plus bu, right? That corresponds to a linear time invariant differential equation. And if things are not time varying, they're not time invariant, then it turns out your system is changing with respect to time, and it might work here, but it's totally screwed up down the road a little bit. And so it does turn out that fuzzy Mamdani control, it works very well on linear induction machines, does very well in the tracking, for example. Okay, any questions on that? And I want you to notice that I've presented this whole idea of Mamdani control in a single lecture, right? It didn't require an entire course in Laplace transforms, pole zero plots, and root locus plots. I'm forgetting some of the things. X dot is equal to AX plus BU. It didn't require any of that matrix, well, a little bit of matrices, for example. Let me tell you some of the problems associated with this. Any questions, by the way, before we talk a little bit more about this?
I have one, and the question really only applies if there's an easy answer. You mentioned earlier that for the and or operations on fuzzy sets, you can kind of choose the kind of operation you want to do. Yes. And you mentioned that using the min and max for and or respectively had its advantages. Are there any simple examples of those advantages that you could mention?
Well, here's what we'll find out. This is interesting. We're going to look at different proofs. I'm sorry, different variations in the ands and ors. And you would like the fuzzy logic so that it always met the boundary conditions, right? Well, the fuzzy logic didn't meet the boundary condition in the law of excluded metals and the law of contradiction. It didn't meet the boundary conditions there, right? So maybe if we used a different and or, that we can meet the boundary conditions. But guess what? It screws up somewhere else. And it is literally provable that you cannot get an and an or which satisfies all of the different criteria that you would like satisfied. And I'll get into the specifics of that later on. So the min and the max is very good. And the only place that I'm aware of where the boundary conditions fail are the law of excluded metals and the law of contradiction. If you change your min and max to meet that, not your min and max, your union and intersection, to meet that, it turns out you screw up somewhere else in your calculations. You don't get, for example, associativity. You don't get De Morgan's law might not work. Okay, so it's kind of like whack-a-mole. You know, you come up with something, and if you whack one of the conditions down to make it work, another problem comes up somewhere else. And we'll elaborate that on that a little bit more later in the course. Any other questions? Okay. One of the things I wanted to point out is something very interesting. You notice here, this is this GPA example here. We had GPA and GRE. We had two antecedents, right? And each one had 3 fuzzy membership functions for a total of 3 squared rules. So if we had these 3 different conditions and you went to an expert, you would have to query that expert 9 times in order to fill in this matrix, right? Suppose instead, suppose we wanted to get more fine-grained. Suppose that the GPA instead was said to have maybe 10 membership functions and the GRE had 10 membership functions. How many rules then would we have to query? How big would the matrix be? 10 times 10 or 100, right? Now think of additional criteria. What if we included extracurricular activities, which is kind of subjective? You looked at their record and you gave it a score maybe of 1 to 10 on the degree that they were involved in extracurricular activities. And so we all of a sudden we have a third antecedent. And suppose that had 10 rules. So we got a GPA with 10 rules, we got a GRE with 10 rules, we got extracurricular activities with 10 rules. How many numbers have to be filled in? 1,000, right? 10 times 10 times 10. This is the curse of dimensionality, and it rears its ugly head in a number of different places. Here is one of them. Now, it does turn out, and we will study this later in the course, that this really brilliant guy from Boeing named Combs came up with an idea on how to mitigate this and keep the number of tables that you had to fill in, keep it to a minimum. So you wouldn't have to do 1,000. So you can have lots of variables, but you see every time you add a variable, you add a different dimension in the rule table that you have to fill in, right? So that's true. This is true of any expert system. As you get more and more complicated, you got to query the expert more and more and more in order to fill in everything. So that's the rule of, or the curse of dimensionality, I should say. I used to be at the University of Washington for a number of years, and one of the big places that they have in the University of Washington is a good relationship with Boeing, because Boeing is largely in Seattle, Washington. They've been a presence there before Microsoft and Adobe and all of these other. Amazon, I think, is centered in Seattle. So they were big guns in the block. So we did a lot of work with Boeing, and one of the things we did is we came up with a fuzzy automatic landing for airplanes and automatic braking for when the plane hit the ground. And there's where I learned that you have different derivatives of distance. What's the first derivative of a distance with respect to time? It's velocity, right? You know what the second derivative is? That's acceleration, correct? Right? You know what the third derivative is called?
Jerk.
Jerk. That's right. That's right. And then the next derivative. By the way, you get jerk, and this is one of the things that they were trying to get rid of. When that plane lands, do you ever notice it hits the runway and doop, your head kind of goes back? That's a change in acceleration, right? So that's jerk. And then you take the derivative of jerk, you get snap. And then the derivative of snap is, anybody want to guess? If I give you the second one, you'll get the third one. The derivative of it's crackle.
No way.
Way. And the derivative of crackle is pop. So those are all the derivatives that you try to get rid of. Anyway, it turns out that the history of these automatic braking systems for airplanes had a long sordid history. They worked, they were designed, and then they were mechanistically improved. In other words, people came along and said, well, it doesn't do this. Well, let's put a Band-Aid on it here to make it work a little bit better. And then some more things were figured out. And they said, well, let's put another Band-Aid on it right there. So I worked with these guys at Boeing, and we came up with a fuzzy control for automatic brakes. And we were really excited about it because they had this big test bed where they had all these mechanical things where you could simulate all of these things, not on a computer, but in a laboratory setting. And I got a call one day, and the guy I was working with said, it's dead. I said, what do you mean it's dead? He said, the whole fuzzy automatic braking is dead. And I asked why. It worked a lot better. It was provably better. And then he says, well, the people far up kicked it because nobody wants to fly in an airplane whose braking system is based on fuzzy. So that was a consequence. That was a consequence of naming this fuzzy. Zod has been confronted a lot about this. He says, no, I probably would still name it fuzzy. But people have tried to make it more politically correct. Sometimes it's referred to as soft logic. And sometimes you'll see in the literature, instead of fuzzy logic, you'll see soft logic. But still, there's the IEEE transactions on fuzzy logic or fuzzy systems. There's the International IEEE conference on fuzzy systems. And so fuzzy still makes its rounds. And it's like a lot of things, it's beating down the presuppositions that the word fuzzy means. I remember listening to a debate one time, and it was, gosh, who was it between? I think it was Bush and Clinton. the senior Bush, and Clinton was saying all of Bush's economics was just based on fuzzy arithmetic. And I looked up on my bookshelf, and there is a book. It's called Fuzzy Arithmetic, where you can do arithmetic using fuzzy logic. So you can see that the crossover of the idea of fuzzy has not been the easiest road, but it's still out there. People are still doing it. Okay, any questions at all?
So with our sort of system of fuzzy inference, is there a way from sort of going from maybe some model of how the system to behave, how the system should behave, to sort of the min-max statements?
Well, in fact, yes. In fact, we did some work. We weren't the only ones. A lot of people did some work on automatic tuning of fuzzy systems. You come up with a fuzzy system, and then you apply it to a search algorithm that searches for the proper parameters and proper way to do things. And that search algorithm then zeroes in on the final design without a human in the loop. And that, that's possible. That's possible. Basically, you have to give it a lot of training data of what you want your input to be and what you want your output to be. And if you do that, it's almost like a neural network, right? You define what your inputs are, you define what your outputs are, and the parameters of the fuzzy system could be adapted. And there's a number of parameters that could be adapted in the fuzzy system. One, for example, is the width of the fuzzy membership functions that can be adapted. There's also, do you have too many rules? Do you have not enough rules? And we did a thing where we started with a whole bunch of rules, knowing that it was too many. And then we began to prune it back by using fuzzy, I think we called it fuzzy pruning and annihilation, where some of the unnecessary fuzzy membership functions went away. So yeah, there's lots that you can apply to this with conventional search in order to fine tune the fuzzy system if you have definitive idea on how the fuzzy system is supposed to work in the end. And you have to have corresponding input output data. Okay.
Just kind of a follow-up to that. Do you know if there's like a way to sort of that these systems integrate into like the framework of like, for example, kernel-based machine learning or support vector machine?
No, this has nothing to do. Kernel-based is an alternative to neural network that a guy named Vapnik came up with. Vapnik, and I can never pronounce the second name, Chernobylenko or something like that.
Chervonenkis, I think.
Yeah, Chervonenkis. Okay, and they came up with this, and no, there's no relationship. It's an alternative technique to neural networks for training stuff. Ironically, I don't know if anybody here knows, but I haven't seen the VC approach being used for deep learning. There are, I don't know if it generalizes. A lot of these approaches suffer from this idea of the curse of dimensionality. And I don't know if the VC approach does it or not, but yeah, the kernel-based techniques. Yeah.
Yeah.
I haven't seen it. It's like a lot of things. There was a big bump in excitement about the VC dimension. Everybody said it was going to kill neural networks, but then they realized the complexity had just been moved from one place to the other. The other place that it was moved was in the choice of the kernels. And that was the new roadblock. And I'm not sure how well it generalizes. We're going to talk about something in here called particle swarm, which is another way to train neural networks instead of something called error backpropagation. I'm getting ahead of myself, I realize that. But you haven't seen particle swarm being used in deep learning. It turns out that it doesn't scale very nicely. I'm not sure about the kernel-based methods, but I wonder if they would be applicable to deep learning. I don't know what would be the correspondence, the operations you need in, say, deep convolutional neural networks. I don't know what those would be. So no, this is totally different than kernel-based learning.
To answer your question, there's actually a paper out there. It's kind of interesting called, if you Google every machine learning model learned by gradient descent is a kernel machine. There's actually something the mathematician came up with called
Okay. Okay.
the path integral kernel.
Colin, you got to quit being impressed by headlines. This sounds like something that somebody published in order to get some attention, and there's probably a modicum of truth in it, but I don't know. I'm not too excited even by the thought. It's like we were talking about Alan Turing and Alonzo Church both came up with different computer models, and they were shown to be equivalent, but nobody cares anymore. Nobody cares anymore because everybody looks at Turing, and the Turing machine is what survived. So yeah, it's interesting historically. It's interesting on a technical level, but I think we had a similar thing with Heisenberg and Schrodinger, right? They both developed a theory of quantum mechanics. Heisenberg, let's see, Schrodinger came up with a partial differential equation that described quantum mechanics, and Heisenberg's was more of a matrix sort of approach, and they showed those were equivalent, but I just wonder about the consequences of that. So, okay, any other questions? Okay, let's then talk about a little bit more different, something different, a little bit more diving in. This is from a chapter, and I've made a link to it on the Google Sheets. It's a chapter by Clear and Fogel and no, not Fogel, Clear and Folger. That doesn't sound right. Let me open it up. I do know one of the authors is George Clear, K-L-I-R, who is one of the pioneers in neural networks. Not neural networks, but in fuzzy logic. And there is stuff there for him. So anyway, this chapter is, a link is provided in the Google Sheets. So with that, I'm gonna pin myself, and I'm going to start my video camera. For my overhead. Okay, everybody can see my overhead here. Okay, if I get off screen, let me know. I think I'll probably be okay. We wanted to talk about here the difference between some of the different ands and ors that you can do with fuzzy logic, and Clear and Folger. That's the second person, Folger, just like the coffee. Make a very good case for it. The first one we'll look at is the complement. See, I'm staying in line better. And the reason I screwed up in the beginning is I was looking at the screen instead of the piece of paper. The complement is something which does what? The complement maps the interval of 0 to 1, and it maps it to the interval 1 to 0. And what we did for Zada is we had the complement of a membership function was equal to 1 minus mu, right? 1 minus the membership function. The question is can we extend this to something which is more exciting? To do that, Clear and Folger look at axioms. It turns out the good math, if you're into math, and some engineers are, but it's performed axiomatically. So let's look at some properties that we would like to have for the complement. And this would be, of course, the fuzzy complement. Number one, this is kind of axiom number one, if you will, is that the complement of 0 should be what? Tell me what the complement of 0 should be. 1, yeah. And we would like the complement of 1 to be equal to 0. So this, if you will, is the boundary condition. Remember, we said that we would like all of our operations to reduce to the crisp equivalent. This is the reduction to the crisp equivalent. Axiom number 2. Let me see if I can position myself. I'm just figuring out how to write here. Axiom number 2 is it should be monotonically non-increasing. For example, if we have the complement, if we have mu, and then we have the complement of mu, then what is that equal to? The complement of mu is equal to 1 minus, right? The original mu. And if we look at that, that turns out to be a nice line which goes from 0 to 1. Correct? It's 1 minus the other one. This is the function, if you will, of 1 minus x. So what we're saying is that in general, it has to be monotonically non-increasing. So for the first 2 axioms, as long as we, first of all, cement these 2 guys down, we could also have something which comes down like this. That would be okay because that's monotonically non-increasing. Or we could have another complement which goes like this. That's monotonically non-increasing. So all of those are okay and meet the first 2 axioms. The third one is that we would like it to be continuous. In other words, we don't want a complement to go up to a point and then do a big jump. So it needs to be continuous. 1 minus x is continuous. This curve that I wrote here is continuous. This is continuous also. So we would like it to be continuous. And here's a rough one. This one's very interesting. This is number 3, by the way. Number 4 is, I'm going to teach you a nice word here, is involutive. Anybody know that word? Yeah, me either. It's not something you use regular every day. What happens if you take the complement of a complement? What should you get?
The original.
Yeah, you should get the original back, right? The complement of a complement. That's what involutive means. So if we take the complement of the complement, if we take the complement of, say, a number A, we should get back A. The complement of the complement gives us back the value of A. So that's kind of a restrictive one. Notice that this works for 1 minus x, right? This works for Zada's 1 minus x. Involutive works there. So the question is what is a possibility for some of these different results? We're only going to have 4 axioms, but one of the results is by Sugino. Now, Sugino was the chap in Japan that recognized the importance of fuzzy logic and was the academic pressure to get Japan to apply a lot of these things to practice. Not only that, he was a very gifted mathematician. Now, a lot of these complements are parameterized. The Sugino is parameterized by a lambda. And we're going to have a complement of A. And again, lambda is a parameter here. And it's equal to 1 minus A divided by 1 plus lambda A. Now that doesn't, that looks kind of innocent, but you'll notice, first of all, what does it become if lambda is equal to 0? It becomes the zeta complement, right? A 1 minus A. Now here is the interesting question. Does C lambda of A equal A? I mean, this is the rough one to get. Is that intuitive for anybody? It isn't for me. But indeed, we'll see that that's the case. I'll probably assign this to you as a homework to show that the Sugino is involutive. I will show you a copy of the Sugino class. This is from the Clear and Folger handout. I think this should probably come through. And this is what the Sugino class looks like. And so we have here the C lambda of A, and here we have A. So you notice the lambda is equal to 0 is just what we said. That is specifically the zeta complement. And then as lambda gets bigger, this complement begins to go down. And you notice that it satisfies all the axioms, right? It's decreasing, it's continuous, and it isn't apparent, but it's involutive. As lambda goes negative, the complement begins to bulge. So this is something that you could use for a fuzzy complement if you wanted to. And one of the parameters that could be used, for example, in tuning a fuzzy system is to use a Sugino complement and to fine tune the lambdas. You could actually do a search for the lambda that makes your system work the best. So that's one of them. Another one is a so-called Jaeger complement. Ron Jaeger is a very interesting guy. If you look him up on Wikipedia, he has like a H index of in the hundreds. I mean, the guy is, he's a pioneer in fuzzy systems. Very interesting gentleman. He's severely handicapped. He lives in New York City. He loves New York City. In fact, he was offered a position for an endowed chair in Florida, and he was negotiating with them, and he said, yeah, this is fine as long as I can come back to New York once a month for a week or something like that. And his negotiation failed. So he never got his position, But he did all sorts of things. I worked with Jaeger on a conference on, it was called CIPHER, Computational Intelligence and Financial Engineering. And it was the application of computational intelligence to markets. And people that did financial engineering are and were very interested in the markets. Now, you might think that they're interested in the market to forecast the market. No, you can't forecast the market. Forget about using the market or forecasting the market. But there are other places that one can use artificial intelligence in finance, which is very good. Anyway, here's the Jaeger class. The Jaeger class is that C. Now, the Jaeger class is parameterized here by a W. And I'm really doing good staying in the lines, huh? Whoops. Let me rewrite that because this is kind of. And again, you choose a value of W, and any of those is a possibility. When does this become, by the way, the zeta complement for W is equal to what? What's the Zada complement?
I think that'd be when either, if that's a W or omega is equal to 1.
Yeah, W. When W is equal to 1, then it's just 1 minus A, which is the Zada complement, right? So both the Sagino and the Jaeger complements are have the Zada complement, the Zada complement as a special case. Here is the Jaeger class. This is also in that handout from Clear and Folger. This is the two classes of fuzzy complement. The top one was the Sagino. This is the Jaeger. And the Jaeger, for example, we said for W is equal to 1 is equal to the 1 minus X, which is the straight line here. And omega is equal to 2, and other places gives us some other things. So those are possibilities in using different methods for complement. The question is, does this extend to the and an or? And yeah, it does. There are generalizations there. Does this make sense that this is involutive? I mean, would you expect that would you think that this would be true? Again, looking at it, it isn't apparent. I don't think it's apparent. Do you think it's apparent? I don't think it's apparent at all. But if you put a pencil to it, you'll find out that's the case. That indeed it is involutive. Okay, well, that's it for the day. We'll talk about the intersections and unions next time, and we'll find out that those also have generalizations. And just like with the Sagino and the Jaeger complement class, these generalizations typically have Zada's min and max as special cases. Any final questions? Okay, well, thanks, guys. Appreciate it. Thank you for your attention.
Thank you.